Hi everyone and welcome. My name is Dario Paccagnan and I'm an assistant professor at Imperial College London. The work I present today is entitled In Congestion Games, Taxes Achieve Optimal Approximation and is joined together with Martin Gairing from the University of Liverpool. I would like to start by giving you an overview of what you would find in the remainder of this video. More in details, we consider the problem of minimizing social costs in atomic congestion games. Atomic congestion games are a widely studied class of problems. They were introduced by Rosenthal 50 years ago, and they're typically utilized to model selfish resource allocation. Within this context, we provide two key results. First, we provide a tight NP hardness of approximation. Specifically, we show that minimizing the system cost is NP hard to approximate within a factor which we give in our work, and which depends solely on the class of resource costs utilized. And we are interested in this result as it gives a bound of what can be achieved by any tractable mechanism aiming to incentivize good behavior. And so complementary to this, our second result shows that we can in fact compute one such tractable mechanism, a taxation mechanism, whose performance precisely matches the hardness factor. So specifically, we start from the unincentivized setting and we introduce taxes so that the equilibrium performance improves and improves and improves and improves up until we match the hardness result. As a consequence of this and the fact that correlated equilibria can be computed in polynomial time, we derive the first known polynomial time algorithm with optimal approximation. All in all, the work can be summarized as follows. Judiciously designed taxes can be computed in polynomial time and achieve optimal approximation. In addition to that, no other tractable intervention, there has been a lot of work in information provision, cost sharing rules, and so on and so forth, can ever improve upon this result. Now, I would like to substantiate these claims, and to do so, let me start by providing you with the standard congestion game model. In a congestion game, we are given a set of resources, for example, the set of edges here in the graph, and each resource is associated to a resource cost. This resource cost tells us how costly it is to utilize that resource as a function of the number of agents currently selecting that resource. Resource costs are oftentimes also referred to as latencies. In addition to that, we are given a number of agents, for example, the blue and the red cars, agents or players. And each agent is given a set of possible allocations, for example, the set containing the different paths here for the blue car and for the red car. Once every agent decided on her own allocation, each agent incurs a cost, and that cost is nothing but the sum of the resource costs over the collected resources of that agent. We will then measure the system cost. We will then measure the quality of an allocation utilizing the system or social cost, as typical in the literature, which is defined as nothing but the sum of each and every agent's cost, and you have a very simple example here. As I anticipated, congestion games have been widely studied, and they are utilized to model a number of different problems. A non-exhaustive list of applications is here. They've been utilized to study routing, both within road traffic networks and internet networks, sensor allocation, scheduling, minimum power problems, and many more. Having said that, the focus of this talk would be on minimizing the system cost. And so I would like to start by providing you with the first main result. To do that, let me start by giving you, by recalling what are the main related works. As I said, the problem has been thoroughly studied, so I would only focus on key references here. And I will denote with the min SC the computational problem of minimizing the social cost. Myers and Schultz are the first one to prove hardness of this problem, and the problem also remains hard in a much simplified settings when all latencies are linear functions. Now, regarding inapproximability result, the best known result is that of Roughgarden, where limited to the special case when resource costs are polynomial of maximum degree d, Roughgarden shows that there exists a beta such that minimizing the system cost is NP hard to approximate within the factor you see here. Now, this is not a concrete computational lower bound in the sense that beta is not explicitly defined. It just gives us an idea in terms of how this approximation factor grows as a function of d. So all in all, there is certainly no tight computational lower bound, and I would also argue that the results by Roughgarden doesn't really provide a concrete bound. Our first main result instead completely settles the question. Specifically, we will prove the following statement. We show that in congestion games, even in the simplified case where all resource costs are identical, and they are identical to some cost function I will call B, minimizing the system cost is NP-hard to approximate within the factor you see here. So first of all, let me just clarify that this is well defined in that we are supremizing a function which is a function of only x, and also observe that the numerator is nothing but the expected value of the denominator, where x is replaced by a Poisson random variable of parameter x. Now, naturally, this result holds for these classes of problems, and therefore it applies to richer classes of problems, which are typically studied in the literature. So, for example, the result typically already applies to the case where resource costs are actually obtained not by a single function, but by a combination of multiple functions. And in this case, clearly the inapproximability result, the inapproximability factor, is at least as high as the worst one produced by each and every of these functions separately. So it's at least the maximum over j over obj. Now, why is this interesting at all? Why am I talking about this extension? Well, utilizing this extension, one can immediately get a result for polynomial congestion games, which are amongst the most well-studied problems. So as a simple corollary of the following theorem, we get this statement, where we learn that in polynomial congestion games of degree d, the inapproximability result precisely equals the d plus first bad number. And this is obtained by simply evaluating the expression rho b upstairs, where b is substituted with a polynomial of degree d. Now, bad numbers can be easily computed. In fact, you need just to look up at the table. And so, for example, this tells us that in affine congestion games, minimizing the social cost is NP-hard to approximate within a factor of 2, and so on and so forth. Now, taking a step back, this constitutes our first main result, and I would like to spend a few minutes on the main ideas behind the proof. For the technical details, I suggest you take a look at the manuscript. So the proof goes by a reduction from a problem called gap label cover to congestion games. And we will make use of a gadget, of a tool, which we call partitioning system. Now, gap label cover problems have been informally introduced, implicitly introduced by Feige in his famous threshold of log n paper. And they've been more recently worked out by Dudicis et al. In this HGAI paper. In a gap label cover instance, we are given a bipartite graph, as the one you see. We are given a palette of colors, say red and blue, and we are given a set of constraints for each and every edge. Specifically, these constraints tell us how we must choose the color of the right node as a function of the color we put on the left node. Typical problem in this setting is that of coloring all the nodes so that all constraints are satisfied, as you can see in this example here. Now, very informally, what Feige proves is the following. He shows that it is NP-hard to distinguish between there exists coloring that satisfy all possible constraints, or no coloring can even satisfy a small fraction epsilon of the constraints. So we will build on top, the proof builds on top of these hardness results, and we reduce gap label cover to congestion gain. In addition to that, we utilize a partitioning system to induce the gap that we require. So what is a partitioning system? A partitioning system was, again, introduced implicitly in Feige, but then more recently presented by Barman in this recent Stacks paper. So a partitioning system is constructed as follows. We are given a set of resources, and every resource is associated to a cost function B. Think about B as the same B from the congestion game before. We are then given a collection of subsets of R, and these subsets are indexed by I and J. Now, these subsets have a key property, and the property is the following. If we think here about each column as being a different agent in the game, and if we think about each and every row as a possible allocation for that agent, the property is the following. Whenever agents select allocations aligned in the same row, the system cost is very low. While on the other hand, if they select scrambled allocations, and specifically allocations so that no two allocations belong to the same row, the system cost is very high. Specifically, the ratio between these two numbers equals the inapproximability result we aim to achieve. And so our proof goes by reducing gap label cover to congestion gains and utilizing the partitioning system to induce precisely the gap that we want. Having said so, take a look at the full paper in case you're interested to learn the final details. I will then here take a step back from the first main result and instead move towards the second main result, where we will show how to design polynomial time algorithms with optimal approximation. To do that, I need to recall two important points. So first of all, let me recall that the price of anarchy is typically utilized to measure the equilibrium performance and is defined as the ratio between the system cost of the equilibrium and the optimal cost. Nevertheless, computing in equilibria is not really something we can do in polynomial time, to the best of our knowledge, but we get immediately reminded that correlated equilibria and coarse correlated equilibria can indeed be computed in polynomial time, for example, either through the famous ellipsoid against hope algorithm or through no-regret learning. And so putting these two observations together, one starts thinking about the price of anarchy as the approximation ratio. That is, if we can compute an equilibrium allocation in polynomial time, and that equilibrium allocation has good performance, has good price of anarchy, we immediately inherit an approximation ratio in polynomial time as good as the price of anarchy. Because of this reason, but also because of a number of other reasons, there's been a lot of work on trying to improve the price of anarchy in congestion games. And there are a host of possible applications, of possible ideas and approaches. I'm really just limited here by the size of the slide. Quite interestingly, I would say, we will be able to show that a simple mechanism, such as a taxation mechanism, is able to reduce this price of anarchy to the point where we match the hardness factor. And this will constitute our second result. Before going there, let me talk about related works, both in terms of polynomial time approximability and taxes. Again, here just key references. The best known approximation for minimizing social cost is that due to Makarichev and Sviridenko, and achieves an approximation factor that you see here. Now, this is reminiscent of the inapproximability result from before, but it's not exactly equal because of the red bits. And this is enough to make sure that there is a certain gap between this polynomial time algorithm and the hardness factor. On the other hand, limitedly to polynomial case, Karagiannis et al. First and Bilo and Vinci later show that well-designed taxes achieve a price of anarchy equal to the Bell number, though this was not known to be the hardness of approximation. And so all in all, there is no matching approximation in general. The first result is not tight. The second result only applies to polynomials. And so our second contribution fully resolves this second problem. Specifically, we'll prove the following statement. And I'm going to state the theorem again in the simplified case where all resource costs are identical, but the result generalizes. So in this setting, and with standard assumption, the claim is that we can compute taxation mechanisms in polynomial time, ensuring that the resulting equilibrium performance is upper bounded by the inapproximability factor plus epsilon, where we can take epsilon as small as we please. With a little bit of work here, one extends the result to the case of combination of different functions, and so one needs to replace rho b, again, with the worst case rho b, max over j, rho bj. Perhaps more interesting or equally interesting than the theorem is the corollary. As coarse correlated equilibria can be computed in polynomial time, we immediately get a polynomial time algorithm. So specifically for any epsilon larger than 0, we can compute an allocation that essentially achieves optimal approximation plus epsilon, where epsilon can be made as small as we please. And the idea here is simply that of designing taxes in polynomial time, computing an equilibrium in polynomial time, and therefore inheriting this approximation which you see here. In the last few minutes, I'd like to walk you through the main ideas and then to conclude. So the main ideas behind this proof go as follows. First of all, let me remind you that the social cost can be rewritten in the following form, as you can see here. And let me also define a slightly modified version of the system cost, where this expression is replaced by its corresponding Poisson expected value. Now, the idea behind taxes is as follows. We start from an original resource cost, and we want to modify that resource cost. So we want to design B bar, the new resource cost. The tax will then be nothing but the difference between these two quantities, where we will make sure that the difference is non-negative. Now observe here that this modified research cost depends again on the congestion level, but also on an exogenous parameter. And this is something we will optimize over. So there are two key ingredients in the proof. First of all, we would require B bar, the modified cost, to solve a crucial recursion. The details are in the paper, but essentially this recursion will give us the complete expression of B bar. And we will then utilize a certain specific V, specifically that V that solves the continuous relaxation of the minimum social cost problem, minimum social cost where we utilize the Poisson expected value. Now, one can then just put everything together. I'm going to do so at least for Nash equilibrium, but the result generalizes. So first of all, utilizing Nash inequality and the crucial recursion, one can move from the original cost function to the Poisson cost function. And this is the most technical part of the proof, so I'll skip this for you. At this point, one observes that V bar is actually defined as B minimal for this cost function. So we can move from V bar to anything we want, say the optimal allocation. And then by just recalling the definition of rho, which is defined as the worst ratio between this quantity here and this quantity here, we can just move back to the original cost function, thus concluding the proof. Having said so, in the last minute, I'd like to take a step back and to conclude. So in this work, we consider the problem of minimizing social cost in atomic congestion games, and we provided two complementary results. On one hand, we have a tight NP hardness of approximation, and on the other hand, we've showed how to design polynomial time algorithms with optimal approximation through the design of taxes. A few comments are in order. First of all, I do find it quite interesting that utilizing incentives on top of selfish behavior actually achieves the same performance as that we could have obtained if we had full control over the system. In addition, I also find interesting the fact that a simple mechanism, such as that of taxation, is enough to precisely match this hardness factor. On the other hand, let me observe that the taxes we defined require the solution of a centralized convex optimization problem, which might be something undesirable. But we can also get away with that. In the recent work, we showed how to do so at the price of losing some amount of approximation factor. Finally, the main result number 2 extends to network congestion games, while main result number 1 induces a general congestion game, not necessarily a network congestion game. And so that reduction is still an open question. I would like to thank you, and I'm more than happy to take any question.